Welcome everyone to this last CVAS seminar of this winter series. And I'm really glad to see many of you joining, because it's been a great journey from the shortest timescales of fluctuations at the Earth's surface to all the way to the age of the Earth, really, in the last talk. And it's my pleasure to introduce also our speaker for today, which is Shaun Lovejoy, who is going to really build this bridge from the smallest spatial and temporal scales to the long time scales. And maybe a few words about Shaun. Shaun studied physics in Cambridge in the UK, and then went on to obtain a PhD in physics from McGill University. And it seems like you really like McGill and you like Montreal, because then you basically spent your entire career there and you've been really productive and successful in building the whole, contributing to the whole field of nonlinear geoscience, I think. And so in that sense, I would say we're looking forward to your talk on climate variability, Shaun. The floor is yours.
Okay, so thank you very much, Kira. And today I'm going to try and do what I can to stay within reasonable bounds for Zoom conferences. I'm going to try and combine some, first part of the talk will be about sort of empirical look at what I'm calling the details, and I'll explain that, and what implications that has for the future of climate modeling. So be rather brief, but hopefully adequate to get the idea. So, you know, the problem that we have throughout Earth systems modeling and understanding and forecasting is huge ranges of scales. And I'm going to focus on the atmospheric component, the ocean, but you can see in this one picture, in fact, a range of scales of about 1 billion from the turbulent dissipation scale. It's actually less than 1 millimeter, but in this wisp of a smoke, you can see maybe 1 millimeter size structures. And then, you know, clouds looking up from the, say, roof of the physics building in this case. And then here you have a geostationary satellite. And so there are structures within structures within structures over this huge range. And so we shouldn't be surprised that in time, we also have a huge range. In fact, it's much bigger. If we go from the dissipation time scale, which is less than a millisecond, typically, to the age of the universe, we have actually, it's more like 1 billion billion. And just in this one plot here, where I have, you know, paleo data and, you know, there's a whole bunch of different technologies, but so these are supposed to be temperature or proxy temperature series, 1,000 points in each. They've been non-dimensionalized so that the amplitudes are comparable. And you can see here actually a range of greater than 10 to the 17 in this one image here. Come back to that. Okay, so how do we understand that? And there's kind of two extreme ways of doing that. And probably we're going to need both, in fact, but let me explain the two extreme ones first. So here is poor old Van Leeuwenhoek back in the 17th century, and he's looking through the first powerful microscope, and he is credited with having discovered a new world in a drop of water, right? That's the famous phrase. And of course, he discovered microorganisms. And so it may be unfair to him to blame him for this view that Mandelbrot has called this kind of a scale-bound view that we inherited from then, which is that if, you know, every time we blow something up, we zoom into something, we see something qualitatively different, right? So we have this powers of 10 view, which became kind of popular after a famous book in the 1950s. And then there were films. There's even a powers of 10 app now for your iPhone. So you get the idea, every power of 10, every factor of 10, you get something totally different. Okay, so that's this, what Mandelbrot called a scale bound view. But, and so that was really, I think, what was behind this famous spectrum here by Murray Mitchell. Mitchell came up with this, he published this in 1976, which was sort of the dawn of the paleoclimate revolution, right? We were starting to get first ocean cores, ice cores, and understanding in a quantitative way some of the deeper past. But he knew that, you know, the data was pretty primitive at that point, so he called this an educated guess, right? So it was, you know, he tried to put all the things, the different processes that he thought were important. You know, obviously there's the daily cycle here, and there's the annual cycle spike. So this was supposed to be a spectrum. And the gray part here is what's called the background. So it was really supposed to be the uninteresting stuff, and you're supposed to focus on this here. We have Milankovitch cycles that were already, of course, known at that point, although it was just starting to be clarified. But anyway, you can see a huge range of things. But the key point is that you're supposed to be focusing on a few narrow range bumps here in the frequency domain, okay? But Mitchell did realize this was just an educated guess. Okay, so that educated guess was sort of revamped and remodeled. So this is a kind of an extract, in fact, of the previous that's been kind of clarified and made a bit more beautiful. First published by Michael Gill in 2002, and then reprinted again just last year. It was called an artist's rendering. Okay, so we went from an educated guess to an artist rendering, and this is still presented as being the way we're supposed to be looking at things. You know, this gave way in 2000. Well, it was before 2015, but it was 2015. I took this plot off the NOAA Paleo Data website, and they admit that this was inspired by Mitchell, but they've removed the quantitative part over here for the variance increasing. But, you know, and they made the artist's impression even more kind of vivid, with the background now is absolutely zero. So the only things that are going on in the frequency domain here are these bumps that you can see. And the idea is you're supposed to have a separate theory and mechanism for each of these bumps. And they call this a mental model. You know, it was very ideological. If you went to the site, it said, you know, this is the way you're supposed to think about atmospheric processes, climate processes. So, okay, so I'll come back to all of this momentarily, but I made a fairly strong criticism of that, as you'll see in 2015 in particular, or 2000, yeah. And so this led to a kind of a change. It was so it was a realization, in fact, that the background was maybe more important than had been believed. But so there's a new paper that just came out by Von Hyde and others, I think it was in January. And what they decided to do was to try to get rid of the background by dividing by their guess at the background spectrum, which is a 1 over omega spectrum. So that means that what we're actually plotting here is omega times the energy spectrum. And they didn't put numbers here, so it's only relative variance. But you can see that it's, you know, it's another artist's conception, and they just call it a conceptual landscape. And okay, so what does that mean? What that means is that the scale-bound view has always actually been quite ideological, right? In the sense that first it started out as an educated guess, then we have an artist's rendition, then we have a mental model, now we have a conceptual landscape, right? But the theme in all of this is that the background details, because that's what they are, as we'll see, they represent all kinds of structures and details and motions and stuff happening. But the idea is that they're not relevant or important, and we can safely ignore them, okay? So, all right, so I want to contrast this with the scaling view here. So this is a bit of a caricature here with Mandelbrot staring through a microscope at the Mandelbrot set, this black thing here. And so if you blow up, you know, a little piece here, a little piece here, eventually you get to a more, well, it's actually a slightly deformed, but basically you get another version of the Mandelbrot set at a smaller scale. And so the idea is that if you zoom in, you don't actually have to get something different, qualitatively different, I mean. So, okay, so So we've seen from the previous that the scale bound view actually hasn't really taken the data very seriously, because even in 2020 we're showing all these plots which are artist conceptions in spite of the fact that we've had massive amounts of data over that time. So all right, so starting actually in the 20s, I'm going to show the idea of scaling, right? That you blow things up and you don't necessarily get something different. So we had Richardson proposing already 1926 that the 4/3 law of turbulent diffusion, which is more or less the same thing as the Kolmogorov law of turbulence. We have area perimeter relations of clouds, 80s. And I'm skipping huge amounts of literature here and stuff just to give you a little bit of a feeling. But now, you could look at all kinds of stuff. These are now spectra, but in the horizontal, right? So you have visible, this is satellite, 1,000 orbits of trim, so there's gigabytes and tens of dozens of gigabytes of data that go into this. So you've got, this is visible wavelengths up here, various, this is the thermal IR here, but from planetary scales, 20,000 kilometers to the resolution of the sensor, you've got, essentially perfect scaling here. Microwaves, it's the same. You could look at aircraft data. This takes us down to less than a kilometer here. And also the reanalyses, and also, in fact, the numerical models. And the numerical models and reanalyses, of course, are nice and scaling because the basic equations don't have a characteristic length over huge ranges. So the equations themselves are, in fact, scaling. Okay, and you can also, by the way, compare this to Mars now, because there are reanalyses on Mars, and you find that actually quantitatively the exponents and everything are quite similar. And that actually isn't too surprising, because this type of scaling behavior, the relation of the small scales to the medium to the large, is, from turbulence point of view, it's believed to be universal characteristics. And so actually there are some differences, Mars and Earth, but they're actually quite minor, in fact, in terms of these exponents. Okay, so so what happens when we confront the educated guesses and the mental models and this and that with real data? So here we have Mitchell again, and here's spectra from actual, this is instrumental data, down here less than, say, 100 years or so. And then we have all kinds of paleo data. And you can see that, I put the blue lines, which are just to, this would be the pure scaling power law in this log plot. So you can see there seems to be something like 5 regimes here that I'm calling weather, macro weather, climate, macroclimate, and megaclimate. And you can see that, compared to the idea of a flat background, you're actually wrong by a rather large factor. It's actually about a quadrillion. And so in the sense, in a way, you have to turn poor old Mitchell on his head and say, if we're interested in the variability, almost all the variability actually is going to be in this background. So the background represents all these details and all these things going on that have been ignored in the essentially educated guess. And similarly, the artist's rendition, well, since it's over a smaller range of scales, it's only wrong by a factor of about 10 billion, 100 billion, I guess, but still rather large factor. Okay, so what you can do, and this is a big step forward, I think, in clarifying things. The thing is that the spectra, there's absolutely nothing wrong with them, right? In terms of an analysis technique, it's an extremely powerful technique that I don't want to discourage anybody from using spectra. The only thing that's wrong with spectra is that the interpretation of the result is not trivial, it's not obvious, and that's why, in fact, people looked at spectra over narrow ranges, from 1 year to 100 years, from 1,000 years to 100,000 years. And in fact, they didn't, often people don't even bother putting units on their spectral axes because, can't interpret it anyway, so why bother? But what that's meant is that they didn't realize that, if you put them together properly, taking into account proper units, that you'd get this massive range, right? So they were kind of constantly looking over tiny little range. 100 is even a small range here. So anyway, so I think what we need is really some a more easy to interpret analysis technique, and that's where fluctuation analysis comes in. And so I'll come back to this momentarily, but if you do that, you can see this huge range of scales now, and these are actually typical in the sense of these are root mean square temperature fluctuations, and all of these numbers, make sense. So in other words, at something like 10 days here, okay, so I'll put these are the scaling regimes that I showed before, so power laws again. And you can see that, where this peak is here, 10 degrees change over, in this case, about 10 days, that's plus or minus 5 degrees. So, this, and I removed the daily cycle. So that's a typical, at this location where this data was taken from, that's a typical change. But then when you go beyond 10 days, turns out that's the lifetime of planetary structures. And so you end up having, you end up averaging, in fact, structures, and you end up having a decreasing variability. Then you get, so I'll put maybe, so this is lifetime of planetary structures. Another obvious significant scale here is over here. The Milankovitch cycles, something like 100,000 years. And there, if you look at this, this means roughly plus or minus 3 degrees. There's a typical change going in and out of an ice age. These are high latitudes, so the global average could be a bit less, of course. And presumably that's astronomical plus something, because if it was purely astronomical, you wouldn't get, this corresponds to a very, very broad peak here, right? And of course, we don't really understand very well why it's mostly 100,000 years periodicity, at least in the last 800,000. And okay, and then, all right, I won't go to the longer timescales. Okay, so, but the point is that all of these numbers make perfect sense, right? And here's the, pre-industrial, industrial, the transition here is not, it depends on the epoch. Okay, so we could compare this view with the implications of, say, this is the NOAA view. So if you say that the background is a white noise, then a white noise on this plot goes down like this. So what it would mean is if the NOAA picture and if the Mitchell picture and were correct, that actually they would be saying that at 1 million year timescales, the average temperature of the Earth would be fluctuating by, say, 10 microkelvins, right? So if we had looked at everything in real space with fluctuations, it would have been obvious that we were really badly wrong. So again, nothing wrong with spectra. It's just the way that, it's the interpretation. So just the last point here, coming to this conceptual landscape versus data, well, it's a bit tough here. The best I can do to try and put real data on is to put in power laws, which now look like this, because this is now a linear plot in the vertical, log in the horizontal. You can use the fact that this has an equal area property. So the area under the red, which are basically the same scaling regimes as before, should be the same as what we have here. And, these spikes, daily spike, annual spike, this is obliquity for this period, 800,000 years to 2.5 million years in the past. It goes way off scale here, but it still doesn't seem to capture things very well, although clearly by dividing through by this background 1 over omega, it does a better job, but it's still not very satisfactory. We could also look at space-time, right? This goes back to, they're called Stommel diagrams, because Stommel first proposed this for the ocean. So you have time here, space here, and there you have all kinds of different ocean features and structures that have different, different time scales, space scales. This is the scale-bound view, of course, of the ocean, and this was taken up by Orlansky in 1976 for the atmosphere, and he introduced all of these, macro, this nomenclature. You've got macro scales, mesoscales, microscales, and each one has subdivisions, and so you can see over here all kinds of stuff. Okay, coming back to that momentarily, this again, same view now in 2020, but it's still pretty much an artist's conception, right? So it would be nice to actually put real data on this. So, And one way of doing that is, of course, you could actually take, in this case, I have 1,400 satellite data, infrared. So it's essentially black body emission. It's like basically the data covers something like 12,000 kilometers by 12,000 kilometers by, and then 2 months or something in time every hour. So it's like a cube, 1,400 points on a side. So you can analyze everything. There's millions of ways of analyzing this. The simplest is just to take 1D spectra. So you can go east, west, north, south, time. And if you rescale them right, they all are essentially identical, except there's a bit of a diurnal spike here in time. So what that means is that actually you have this symmetry, which is that if you blow up the horizontal wave number frequency space by, well, it's actually 1 over lambda, some scale, then the spectrum just is transformed like that. Okay, so you have this basic, actually it's an isotropic symmetry here that explains this very nicely. And that in fact corresponds to what you'd expect from if the Kolmogorov law holds in the horizontal for the velocity, right? So velocity relates space and time. And so what you predict, this is a theoretical relation, it says that the lifetime should be the 2/3 power of the horizontal scale times this energy rate density to the -1/3. Okay, so this is essentially the Kolmogorov law in the horizontal. And when you look at the epsilon, you get about a milliwatt per kilogram in the atmosphere. If you average that over the atmosphere, in the ocean, it's about 10 to the 5 times smaller. So you could put this theoretical line on the data and you get these beautiful straight lines here. So in other words, if you start making these Stommel diagrams quantitative and get rid of just a pure artist's conception, then you can explain it very well. And also you find that when you get to the size of the planet, then of course the length scale being 20,000 kilometers implies here a time scale of about 10 days. So it's the lifetime of planetary structures. And here in the ocean, it's more like 6 months. Okay, so you can understand these basic transitions quite readily. Okay, so if I'm going to talk about fluctuations, really what I'm meaning is wavelets. And so here we have a fluctuation that the simple thing is just it's a difference. That's actually called the poor man's wavelet. It just means say the temperature now minus the temperature at a time delta t, delta little t earlier. And this means you take the average, ensemble average over a whole bunch of realizations, say, and so you get this exponent h. Unfortunately, I wanted to go on and tell people about the various meanings of h. It has a whole beautiful history, but I'm suppressing that in the interest of time. But anyway, they get an exponent that tells us how the average fluctuation changes. So we could define fluctuations by differences, as I just mentioned. We could define them by anomalies, meaning you take the series, say in time, and you remove the mean, and then you average over longer and longer timescales. Or what is, in fact, in my opinion, the best solution for typical geodata is to, in fact, do both. That's called the HAR. So the HAR fluctuation is you take the average of the first half of your interval minus the average of the second half. So you kind of combine averaging and differencing. And it turns out that whereas the difference fluctuations are valid, it give you a good fluctuation when h is in the range from 1 to 0. And the anomalies from 0 to -1, the HAR fluctuations are valid over this whole range. And it turns out that that's, in fact, good enough for virtually all geoprocesses. And you can use other fluctuations if absolutely needed. So that's what gives us this. These are HAR fluctuations. And when the fluctuations are increasing, they're essentially differences. So you can easily interpret them. And when they're decreasing, they're essentially anomalies. And so you can also interpret them. And of course, they're extremely easy to calculate, right? Just average of first half minus average of second half, including when the data has all kinds of holes. And I think Nakira and Thomas Lapel and Raphael Hebert have all kinds of software and stuff that, and also on my site, by the way, but anyway, they're also developing this. Okay, so all right, so this is just to show, a wavelet is a kind of there's zillions of possible wavelets. one of the main criterion is that the overall mean has to be 0. So mathematicians like this thing called the Mexican hat, which is actually the second derivative of a Gaussian. But the har corresponds to essentially it's a convolution of your signal with this kind of I don't know, a double step function or something. It looks a bit like the Mexican hat, except it's constants here. The difference fluctuation I didn't put, but they're basically Dirac delta functions going up and down. And okay, so you could write it like that. And in the Fourier domain, the thing is that it corresponds to a filter. And so you can see that the har has the advantage that it filters out the low frequencies to some extent. It filters out the high frequencies to some extent. And whereas the difference fluctuations only gets rid of the low frequencies, the anomaly fluctuations only get rid of the high frequencies. And okay, so I will go on. One thing before I go to the future, I want to just mention the role of intermittency. So this is also important. So here are these, the series that I showed at the beginning. So all these different ranges that we have for temperature fluctuations. What you can do is you can do something very simpler, which is just to take the first differences, right? And you could take the absolute first difference. So you just take one value minus the next absolute value of that, divide it by the mean over the series, and you get these things here. So that means that, you know, whenever you see a spike, it means there's some huge transition in the data on the left. Sometimes these transitions, like here, 1 hour scale, I think this data, well, it's not that obvious. It corresponds to this, but you know, when you see it like this, it's really clear something radical is going on. And if the process was essentially quasi-Gaussian, as is almost always assumed, then these spikes would have probabilities, right? These are the probabilities, 10 to the minus 3. That's what you would expect for 1,000 points. You would never get a spike above that. That's actually what you roughly get in macro weather, say 1 month average data here. Or, but these spikes go way, way beyond, you know, one in 10 to the 1 in a billion probability. Well, they go way beyond that. So these spikes are completely non-Gaussian. And in space, of course, so these are the different time scale. Yeah, you know, you get the same kind of thing, but huge spikes, even more, even in macro weather, which is otherwise in time is the kind of quasi-Gaussian. So one important, there are many consequences, but one of the consequences, you know, and in fact, okay, that's a symptom of multifractality, in fact, but one of the consequences is you get spurious oscillations if you use standard hypothesis testing on spectra. So here's a multifractal simulation here. This is this spike plot. Once again, I just took absolute first differences, and you get these spikes that have very, very low probability levels if it was Gaussian. And now you do a spectrum, and actually I took, example is, okay, did 50 simulations. I took the one that had the most extreme fluctuations, in fact, but you can see that you get many, many spikes. Now this is the mean spectrum, but you get many, many spikes now in the spectral domain, which are way above anything that you would expect with a Gaussian. So here you get a spike that would be, you know, if this was a Gaussian process and you used your normal, the standard, it actually uses an autoregressive process as a kind of a null hypothesis. But if you used all of the standard stuff, you could be as sophisticated as you like about estimating the spectrum. But if your null hypothesis is that the process was Gaussian, then you would say, hurrah, I found a new process with this this frequency corresponding to, you know, 23 cycles per whatever. I'm a hero, I found this. And of course, people were doing that, you know, are still doing this and finding all kinds of spectral spikes. The only thing is someone else comes in with some slightly different data set and they'll find spikes somewhere else. And okay, so you know that's been the history for a long time. So it could easily be just an artifact of this. Okay, so what is the consequence of all of this for the future, right? So we've seen that what some people, what the standard view, the scale bound view says are background. It's actually lots of details, and the details, you know, how are we going to account for them? So in the scale bound view, you ignore the details, but it's not quite the right thing to do, as we'll see. So, you know, here I have this picture, classical picture of molecules in a box, right? You could treat that with F equals ma, Newton's laws. So let's forget about quantum mechanics for the moment. If you go to many, many particles, you really should use statistical mechanics at some point, although molecular dynamics simulations can go up to millions of particles today, follow them each. But at some point, and if you want to forecast, if you want to model climate, weather, et cetera, you really need thermodynamics and continuum mechanics, right? And they don't even acknowledge the explicit existence of molecules and stuff. So, okay, so that is what you'd need to just even make a model of a single vortex. And what you're doing is you're saying that, yes, there are all those details of the molecules, but they're essentially irrelevant, right? They're just not important. So it's not like, you're actually missing something important. If you're trying to model this vortex, you're missing something important if you don't know the position of the molecules. No, you've actually gotten rid of all the stuff that really is unimportant. So it's a big scientific advance. It's not just because your computer is too weak, right? So, but the same thing keeps going, right? So the atmosphere is not just one vortex. It's not even a collection of a small number. It's this more like this spaghetti view with lots of vortices. And so, really we're looking at the collective behavior of many, many vortices. And so again, we have the idea that, most of the stuff is irrelevant, but except that instead of ignoring the details, what we really want are collective laws that tell us about the statistical behavior of lots of them. Okay, so that's where the future of climate modeling comes in, right? So what have we been doing? What we've been doing is chasing the details, right? So, this is just a comparison of the last, actually a bit over 40 years now, right? So the first serious, climate models, this is when we first came up with, if we double CO2, we have a change of temperature between 1.5 and 4.5. It comes from models dating it from 1979, US Academy of Science report, actually in 1979, based on the early climate models. So at that time, we had roughly 10 to the 7 flops of computer power. Today, it's about 10 to the 11 times larger. The algorithms have increased by probably a factor of 1 million or so. That's an estimate by Peter Lynch. So you're using the computer power a lot more effectively. Resolutions have, of course, gone way down. The number of realizations has gone way up. But we're still stuck, 40 odd years later with this same range here for, what happens if we double CO2. Okay, so I'm not, this is just a very tough problem. But what we have, and I think this is, I've claimed that this is, leading to an uncertainty crisis, actually, because this range is too big for policy. We really have to reduce the uncertainty range. And what the mainstream community has been proposing is, right, to 2030 is what we need are cloud resolving models. So I just put some guesstimates here of where we'll be at in 2030 by projecting technology, but we should be able to get down to about 2-kilometer scales for global models. And so we'll be modeling structures that live for about 30 minutes. But, let's say our goal is to work out what's going to happen in 2050. Well, we're going to be averaging huge numbers of these structures, right? Maybe 100,000, factor of 100,000 in time. So we're admitting that almost all of these structures that will be modeled by the world's best computers will, be details that are essentially irrelevant, right? So there's got to be a better way to go. And I'm claiming we need new types of models. So instead of, low-level model, which accounts for as many details as possible, we need high-level models in which most of the details are irrelevant, and we need their statistics. So we go from supercomputers to laptops, in fact. So we need these direct macro weather and climate models. So where are we now? Well, there are approaches to this, right? Going back to Bedico-Sellers, energy balance models. There's other proposals by Leith, Hasselman. There are variations on this. There's been scaling climate response models. And what I'm claiming is the most promising at the moment is a combination of Bedico-Sellers, so energy balance with scaling, and that's this fractional energy balance model. So let me just give you a little bit of propaganda before I finish. So the Phoebe, so that's this new model. it has a deterministic response to deterministic forcing and a stochastic response to stochastic forcing. So if you want to make a projection, say to 2100, then you put in, let's say, deterministic scenario-based and past data-based forcing. And so here's what the equation looks like. So you have a fractional order a storage term. This is the equation just at the global scale, but you can do this at regional scale as well. You've got a relaxation time. You've got a climate sensitivity, right? So, and you can then apply these various IPCC scenarios for the forcing to the future and use their estimates for the past forcing for up to current day. And so, okay, so this is work with Roman Prochuk and Raphael Hébert. So we have, we find that using a Bayesian approach here, we have an estimate of a median timescale of about 5 years, right? Which is comparable to box models. The usual box model, by the way, is h equals 1, standard derivative, and we're finding it's more like h is 0.4. Climate sensitivity is a bit smaller. It's 2.43 plus or minus a small bit, which is compared to then the IPCC 3 plus or minus 1.5, right, for CO2 doubling. It works quite nicely in the past, right? So this is the red is the data. The CMIP5 multi-model ensemble mean is the black, and the Phoebe model is the blue. And so you can see it fits the data quite well, but including we do a reasonable job during the pause or hiatus. In fact, we do a bit better than the CMIP5 that tended to it was overestimating the heating. When you do this, you can do this. This is a moderate mitigation scenario. And we find, in fact, almost total agreement, right? The 90% confidence intervals are practically overlapping, which means that the CMIP5 models support the Phoebe and the Phoebe supports the CMIP5, right? We have two qualitatively different approaches that give essentially the same result. But the key advantage then of the Phoebe is that the uncertainties are actually a lot lower. And of course, they come from, their parametric uncertainty, not structural uncertainty. It's a completely different source. It basically comes from the past data. Okay, you can use this to you can use the high frequency approximation to the Phoebe if you say that the forcing now is internal variability, so it's a Gaussian white noise, say. So that ends up meaning the high frequencies are actually essentially fractional Gaussian noises. You get this Stock-SIPS model, and you can forecast, say, the global temperature like this. So here's Stock-SIPS. This is the Canadian GCM for long-range forecasting. So you can see that we have a better skill. In fact, over the 0 months, that's 1 month ahead, basically starting from now. And the interesting thing is you can actually combine the GCM with the stochastic forecast to get something even better. I won't have time to talk about, but okay. So you can use this for actually very good forecasting. Okay, so but if you apply that regionally, then what you're doing is essentially you're just taking the data at a single point and a single pixel, and then you're using its past to predict the future 1 month, 1 season, 1 year ahead. And you would say, well, something got to be wrong here. Can't I use spatial information? Because I know that, wait a minute, I'll come back to that momentarily. Okay, well, all right. I know that I have teleconnections, basically, right? So I have strong spatial correlations between different pixels, so I ought to be able to use spatial correlations to do better. But okay, the model, though, what it does is it's basically says each pixel I is just a weighted, is the temperature at some pixel I is a weighted version of the past. This is a white noise, and so it has a power law weighting. But the correlation between different pixels is only at the level of the white noise, the innovations. And they are delta correlated. That's very important. That means that the noise that's forcing this is only correlated at time t equals 0. There's no correlations, in the noise between past and future. And so what you can do then is you can do this model and you find interesting emergent properties such as El Nino. So you actually get totally stochastic El Nino. This just shows an actual El Nino event over months. Just concentrate on this region over near Ecuador. So you increase in, anyway, that's an actual El Nino sequence from the 1990s. And this is just a purely stochastic one that was not put in by hand, right? Just as a GCM, if it's any good, doesn't have to put in an El Nino by hand, right? It comes from the dynamics. Similarly, the StochSIPS model doesn't have to put in the El Nino by hand. It's an emergent property of the model, and you can see you get something quite good. You can look at, these are simulated El Nino indices compared to a real one. They're simulated, they're only supposed to be statistically the same, so don't try and compare bumps with bumps, but just you do quite a good job. So can you do better with trying to use the teleconnections? So our model so far doesn't use them. Teleconnections, this is just one representation using network analysis. Here, this is for pressure at 500 millibars. You can do the same with temperatures to see how different points are connected in a network sense. So the thing is that a consequence of our model is that there is no Granger causality. So Granger causality is the precise concept that you need to say. What it says is, if I have a predictor for some temperature at some point, and I add information from some other pixel, does that extra information improve the forecast? And if there is Granger causality, the answer is yes. And if there's no Granger causality, the answer is no. So it turns out that in our model, there is no Granger causality. So, and we can check that. So here we have the connectivity of different regions looking at the temperature. So it's quite high, especially over the tropics, and it's moderate. This is the level of the innovations, but this is at delta T is 0. But when you go to 1 month here, delta T is not 0, then you still have strong correlations in the temperature, but there are essentially none in the innovations. So essentially there's no Granger causality. So what it means is that if I use teleconnections, El Nino or whatever to try and improve the StochSIPS forecast, it's not going to improve. And the reason is basically that the StochSIPS forecast requires a huge amount of data from the past. But all of the teleconnection information is already in that past data, you see. That's the thing. So you've already used the data to make your StochSIPS forecast. Okay, let me now get to the conclusions. I'm sorry, I've gone a bit over, but anyway, I'm there. So what I've tried to explain is that there's this huge problem of details. The details has to do with a huge range of scales. And there are two extreme approaches. One is this scale bound, where every factor of 10 or something, you say there's a new dynamic, but then you end up essentially ignoring the details. But ignoring them isn't the same as saying it's not the same as saying they're irrelevant and I take them into account statistically, right? You're just actually ignoring them. You're pretending that the details are not there. The scaling approach, on the other hand, says, okay, most of the variability actually comes from the collective stochastic dynamic of huge numbers of structures that we can analyze quantitatively, unlike the educated guesses and artist rendition and mindsets and this and that. We can actually, and especially using this fluctuation analysis. And so what the implications are for the future of modeling is, right, in weather modeling, we've been chasing the details basically for a long time. Macro weather and climate, well, so that means we're adding in, essentially we have Earth system models, we've been adding in ocean components, cryosphere, carbon cycle, but the concept here is chasing the details. The more details, the better. And what we're saying is, actually, we should be trying to take things into account collectively, and this can actually be done, and even successfully done. Okay, so this is, I tried to give a bit of propaganda about some early models which are already I think an improvement when it comes to monthly and seasonal forecasts for temperature, and also an improvement when it comes to projections. So I will stop there. And thank you for listening to this.